right, good morning. How you guys doing? that part of the semester. All right, so I wanted to just take a quick look at our schedule. I think we got ahead of ourselves a little bit in a way, or maybe I kind of reworked the way I was doing disinfection, chlorination, and all that. So I might revisit advanced oxidation processes a little bit. But right now what I'm thinking I'll do is, since we started covering kind of the water softening alkalinity stuff last time, and we're going to wrap that up this time, I'll probably move your exam. No, I'm just kidding. Sorry. I'll probably do the Flint water crisis lecture next, which would be on Thursday, and the exam review and the exam will be normal as listed. And then that'll give us a little more space behind that second exam to have a session to review the exam and comfortably cover all the other pieces that we have planned. Okay, so that's tentatively what it's looking like. So we'll let you know if anything else changes. I'll probably post a revised schedule syllabus to Moodle before long. Okay, so last time we left off, we were talking about these equivalent weights and kind of equivalent units in general, talking about expressing some alkalinity or hardness as CaCO3. Talked a little bit about why that's convenient, even though it kind of feels weird at the moment. We're going to do some problems, and it's really a lot like the conversion between mass to moles and moles to mass, but it's done in a way that that conversion is in the background, so to speak. So when we're manipulating these units, we can talk about it, and it's built into the definition of an equivalent weight. So it's a lot like a molecular weight, except we're doing it on a charge basis. And when we say as CaCO3, that implies that that process is already done to an extent. So we talked about that. We've got this equivalent weight of CaCO3, and the definition here is a molecular weight divided by the charge of the cation there, which would be Ca2+. So that would be 100 divided by 2 is 50 grams per equivalent charge, or 50 milligrams per milliequivalence charge. So that's like milliequivalence meaning, or equivalence meaning equivalent number of moles of charge. Okay, so that's what we're talking about. Whereas the equivalent weight of just Ca2+ would be the atomic weight of calcium, which is 40.1, divided by the 2 for the charge. So that would be 20 milligrams per milliequivalent. Okay, so putting that together, we can then do a milligrams of X as CaCO3, and then all we have to do is take the concentration of X in milligrams per liter and multiply that by this 50 milligrams per milliequivalent of CaCO3. And that'll convert our units from milligrams per liter of X, or right here, milligrams per liter of X, to, so when we multiply that across by the milligrams per milliequivalent of CaCO3, divide all that by the equivalent weight of X, that's going to get rid of the X in the milligrams, right? So we have milligrams of X divided by milligrams of X. Those two will cancel, and we'll be left with essentially the milligrams per liter, milligrams of CaCO3 per liter, because we retain the per liter here, and we retain the milligrams CaCO3 here, and the other pieces will cancel. So it becomes milligrams per liter as if it were CaCO3. That's the as CaCO3. Could insert as if it were course, that's a lot to write, so we'll just leave it as simply as. Okay, so that's just a quick rehash of the equivalent weights. I'll make sure if I didn't give you some, I think you probably have to do that on some of the homework. If not, take a look in the book, make sure you can solve some of these problems just to set it up, say, okay, well, what is the equivalent weight of such and such? So you'll have to do that back and forth to an extent. Got a table just to kind of elaborate there. If you wanted to check yourself, make sure you can do that properly. We've got these different cations and anions and other stuff here. We have the atomic or molecular weight, the charge, and then the calculated equivalent weight. So for example, calcium carbonate, we just looked at, carbon dioxide, CO2 aqueous. We have some atomic weight, and the charge here, actually I don't know why it's giving that a charge. I guess maybe they're saying that's H2CO3 once it's dissolved. So then you get 2 H pluses, I think. The magnesium here, the magnesium hydroxide, that Mg will have a 2 plus, so that's why we have a 2 plus charge there, and so we can calculate the equivalent weight there. Okay. So, for an example here, if we have a groundwater that has 100 milligrams per liter of calcium, 10 milligrams per liter of magnesium, express the hardness in units of milliequivalents per liter and milligrams per liter as CaCO3. So this will be good practice, like I was just saying, to kind of force you to do that. Now, I will remind us here at the bottom that the hardness is described or defined as essentially the presence of multivalent cations. So meaning any cation, so positively charged species, that has more than just +1. So H plus is not a multivalent cation. Sodium, Na plus, is not a multivalent cation, but magnesium, which is 2 plus, is, and so on. Okay, so I'm going to give you a few minutes to work on that. I'll rewrite the equivalent weight definition here in a second. And then we'll work that together in a couple minutes. Okay, so as you might see, I've just solved for the milliequivalents per liter, hardness as milliequivalents per liter. That's using the kind of the definition here. We can say that the milliequivalence of some of X per liter, that's the charge equivalence, is going to be X milligrams per liter divided by the equivalent weight of X. So that'll take milligrams per liter divided by milligrams. The milligrams will cancel. Divided by the milliequivalents, the equivalents will come on top. Now, you could have gone and solved for the molecular weight, or using the molecular or atomic weight, solved for the moles per liter of this, and then divide that by the charge to get essentially the moles of charge per liter, and done all of that. But this is sort of a shortcut built in. We can just simply say the milliequivalents per liter is going to be related to that X milligrams per liter divided by equivalent weight of X, because that way it factors in the atomic weights and all that. So that would be the milliequivalents. That's the first part of the question. So what is the hardness expressed as milliequivalents, and then as milligrams per liter as CaCO3. So as CaCO3, what we said a moment ago was that we can simply take the expression in milligrams per liter and multiply that by that 50 milligrams CaCO3 per milliequivalent, and then divide that by the equivalent weight of X. So we'll have to do that for each of them, just like we did the equivalent weights for each. So we can take, for example, the 100 milligrams Ca per liter, multiply that by the 50 milligrams per milliequivalent. Have that right? Yeah, milligrams CaCO3 per milliequivalent. And divide that by the equivalent weight of X, which is 20 milligrams per milliequivalent. So for the calcium, that's the expression. And if we do that, that should be 5 times 50, right? It's 250 milligrams per liter as CaCO3. Did I do that right?
Can you explain why the hardness is 20.82?
Yep, that's just me looking at the wrong number. I guess I had just looked up and I was like, I saw the 20 here or something. Sorry. Good catch. Yeah, so as you rightly note, you just need to add this one and this one. Okay, so then the magnesium here should be the same process. At this time, we only have 10 milligrams per liter of it. The 50 milligrams per milliequivalent is standard. So we could express this as something else, milligrams per liter, as magnesium hydroxide or something. That's possible, but not really something we do. Per milliequivalent. And then divide this by the 12.2. And that should give us, that's 500 divided by 12. Should be 40.98. Let's say 41. Come back. And we would say that's 41 milligrams per liter as CaCO3. So then the hardness alternate way of saying that would be that's 41 plus the 250, so 291 milligrams per liter as CaCO3. Okay, so two ways to express it. They are a little bit like using moles per liter with the milli equivalents. So would be more like millimoles per liter. So we could kind of think of that as 5.82 millimoles of charge per liter. It's one way to express our hardness. And that's, again, charge of multivalent cations, because those are the things that are causing this hardness effect. If we think back on the alkalinity and stuff, the reason that the multivalent cations are so important relates to a couple things. One is the mineralization, just simply mineral deposit kind of stuff. So that's one aspect of hardness that we talk about. That is also, in a sense, related to that acid buffering capacity of water. When we have a lot of positively charged stuff, what's happening, and I'm just going to flip back to our backwards in our notes to what we covered last time. When we were talking about the pH of natural rainwater here, I introduced that charge neutrality concept, and we said in that very simple case, we just had the H plus as the only positively charged thing in solution. And then if we recognize the case where we have some sort of a +2 positive charge here, that's going to have a big impact on the rest of the system in terms of the H plus there. If you change it a little bit, it's not having a big impact if there's +2 things around. So it's really going to mess with how much buffering capacity is present and how the dynamics shift for that. So I'm not being very specific here in the moment, but if we do problems with this, and as we'll see with the softening process, the point of it is that the +2 and +3 charges have a pronounced effect on the charge neutrality. Whereas you can add, specifically with the carbonate side of alkalinity, carbonate can go back out into the atmosphere, right? The CO2 can degas potentially, so in an open system. So when you have some, let's say, calcium carbonate as CaCO3, like we're just talking about, if we add CaCO3, we're adding carbon dioxide, which can just leave solution, whereas that Ca2 plus is remaining, it's stuck there no matter what. So then that kind of has a more permanent impact on the solution chemistry, given that the carbonate system can be essentially added and that associating charge. So having that +2 charge makes it more likely for us to have more carbonate, for example, 2- to balance it out. So there's this whole system. It's kind of not doing it justice talking about it this way, but I'm just going to leave it at the fact that they end up being quite important for both that acid neutralization capacity, allowing for more of this alkalinity and stuff, as well as for the mineralization and all that. Okay, so here are the two ways we can describe hardness then. We've got that. Once we have the formulas and understand where to get our information, should end up being straightforward and possibly intuitive enough that you could just do it without even having learned about it, right? Okay, so solutions a little more elegantly here. It looks like we got the answers right after the correction there. Okay, so one last thing I'm going to add here as we swap to the softening set of lecture slides. When we're describing alkalinity or several of these parameters, our book is introducing another way to describe a concentration, whereas normally we say brackets of X is moles per liter of X. they're going to say, well, sometimes it might be convenient to use these parentheses to do parentheses of x is milligrams per liter of x. Okay, this is a little bit common, I think, but not widespread. So I wouldn't extrapolate this to every time you see it in any sort of chemistry context. But in the case here, what it's going to describe, what they're saying is, well, if we've got alkalinity in moles per liter, and we're describing that as essentially this charge neutrality equation, where we say that the total alkalinity is the bicarbonate plus 2 times the carbonate plus the OH minus the H plus. We could also potentially describe that in, excuse me, I wrote milligrams, I meant to say milliequivalents. Milliequivalents of charge, because again, it's sort of like a mole basis, sort of, but it's counted for the charge. So then we don't have to do that anymore here because it's already accounted for that charge, right? So it's basically just taking that and saying it that way. And you could then, of course, it's also possible to say that's milligrams per liter as CaCO3. Because the as CaCO3 has gone through and calculated for that charge and atomic weight. It has normalized all that already. So both of these cases normalize for charge. And so when we're describing alkalinity here, we could put it in these little brackets and say, okay, the parentheses of alkalinity is the bicarbonate milliequivalents per liter of bicarbonate plus the milliequivalents per liter of carbonate plus the milliequivalents per liter of OH minus and H plus, right? So that's just one other way to simplify a system here. And the other thing I'm going to note while we're on the topic is we're also introducing a definition here for carbonate alkalinity. So we talked in general terms about alkalinity, and so as we move forward, I want to get more specific and describe specific types of alkalinity, whereas alkalinity is, in a way, the ability for a solution or the stuff in solution to cancel out acid. Okay, so anytime we add an H plus, we have, like, this is the equation, we see H plus in here, and if we're adding H plus, we are in some way competing with all of this stuff, right? So it's we'll describe carbonate alkalinity as the amount of carbonate species minus the acid. Of course, we have OH minus there as well. That balances it a little bit, but we understand that's a equilibrium in and of itself. Okay, so that's the end of this set of slides. We're going to pull up the next one. Start back there. Okay. So, another example here. We have a sample of water at pH 10 that has 32 milligrams per liter of carbonate, CO3 2 minus. Find the alkalinity as CaCO3. And I've got here a couple of the equilibrium reaction equations listed, might be needed. So take a couple minutes. I think I've got the solutions to this problem on the next one, but I want you to start off by finding these three pieces here, and I'll get the well, I'll just go ahead and say we can remember that carbon is 12 grams per mole. Oxygen is 16 grams per mole. And we can remember from what we were just looking at a minute ago that because the molecular weight of CaCO3 is 100, equivalent weight of CaCO3 then is 50. Okay. So, what I've done here is I told you about the equivalent weight. It's milligrams per milli equivalent. That was just kind of recall, and I just gave you that. For the carbonate, we can calculate that because we have exactly 32 milligrams per liter of carbonate at pH 10. So that was kind of already known. All we had to do was convert. If we have to answer the moles per liter here, then we can do so. And that's 5 times 10 to the minus fourth, because we take that 0.032 grams per liter, divide that by 60 grams per mole. That gives us that number. To find then the bicarbonate, HCO3 minus, we need to use our equilibrium equation. And given that we are at pH 10, we know that we're in very basic conditions. We're pretty much going to have zero. This will kind of go to zero in terms of that particular quantity. We're not really going to lose much, if any, of our bicarbonate to carbonic acid, the H2CO3. So we're going to ignore that first one pretty much altogether at pH 10. Technically, there's going to be a very, very small fraction that is in H2CO3, but it's going to be such a small rounding error that no one will ever notice, right? We're just going to focus in on that second equation then, which is nice because we have everything known. So that's what I did here. I rearranged to do bicarbonate is equal to H plus times CO3 2 minus divided by that K2 to get a value here of 1.07 times 10 to the minus fourth moles per liter. Now, I had us do this as a little bit of a reminder that, yeah, sometimes we'll need to extract information from the equilibrium in the carbonate system. If we didn't need to do that, then we could probably just work with the equivalent weights and use our alkalinity equation here and go straight from there. So let's take a look at where the book goes to actually solve the problem, and hopefully it'll kind of make sense when we put these pieces together as they go through. So they went ahead and calculated straight up as milliequivalents per liter as CaCO3. So they take this carbonate, that's 32 milligrams per liter, and then they're dividing it by the 30 milligrams per milliequivalent. That's coming from the fact that, and even earlier I noticed that I was a little, that's coming from the fact that we've got CO3 2 minus, is the molecular weight of that is 60, and then we take that, the charge is 2, so 60 divided by 2 gives us that 30. Milliequivalents of charge per, milligrams per milliequivalents of charge. Okay, so that gives us a value there in the as CaCO3 milligrams as CaCO3 per liter value, and then they go back and do the carbonate. Okay, so we could have done that first. I didn't ask for that specifically, so that's part of the equation here. And remember, we have to satisfy the entire alkalinity equation, which I wrote up here, saying, okay, we need this, so that's what they solved for first. Now they're coming back to this, and then we can add in these two and get our answer. And this is a relatively simple case in terms of all we're given is essentially pH, and we have some carbonate. But we're calculating the carbonate alkalinity specifically, so that makes some sense. Okay, so it goes on and describes this equilibrium between carbonate and bicarbonate. And then it's essentially setting up exactly what I showed you. We have that bicarbonate equals CO3 2 minus times the 10 to the minus pH for the amount of H plus here, divided by that K2. And then they report that in millimolar, so we can compare. And let's see, what did they do? Did I do something wrong? Did they do something? So the 4.68 times 10 to the minus 11th. We've got the H plus here, and that 32 milligrams per liter divided by 60 milligrams per mole. Okay. So my answer was 1.07. Their answer is 1.14. So I'm not sure what happened. Maybe I put something in my Excel wrong. Yeah, because this would be then 1.14 times 10 to the minus third moles per liter, right? So I'm off by a factor there. So let me just see if we can find what I did. Oh, well, I need to do 10 to the minus 10th is pH, right? Should be fine. Or is that, did I do,
You did 0.032 grams per liter and they just kept it as 32 milligrams per liter. That's what it has on the solution in the top part.
So they did 32 milligrams per liter, and then they divided it by the milligrams per millimole. I went ahead and converted everything into moles and grams. So I did 0.032 grams divided by 60 grams per mole, right? That's should be the same thing there. 10 to the minus 10, 4.68 times 10 to the minus 11. This is 4.68. Yeah. So the E means one. It's 1 times 10 to the minus 10. That was confusing me as well, but I think that's correct if I look in the formula here. Did I write this incorrectly? I have one too many zeros here?
Yeah.
There we go. Okay, sorry about that. So now we have 1.07 times 10 to the minus third. So I think they may have used different rounding here. So
If you were to do it their way, why didn't it convert the K value to millimoles?
I think that at the end of the day, we're getting, because they also didn't convert this into millimoles. So if milligrams per millimole is the same thing as grams per mole, right? So that conversion doesn't really matter. Those units are going to cancel out in a sense because we're dealing with milligrams up top, milligrams at the bottom. Those will cancel. So the mass values are canceling. And then the millimoles is going to carry through because they reported it as millimoles here, whereas the moles per liter for that and the moles per liter in the units down here are going to cancel. That's what's happening. So that's why they can get away with that. Okay. Sorry for the confusion here. I'm going to fix this here because that was just a calculator error on my part. Yeah, three zeros, and I put 4 in my Excel sheet. Okay, so we have a slightly different number, but it's close enough. I'm happy with it now. Okay, so then they go on and say, basically from there they're going to convert everything into as CaCO3. They already did that for the carbonate. We solved an example for that earlier. You can check their work there. Then they're doing it again for the bicarbonate, multiplying it from that milliequivalents per liter times the 50 milligrams of CaCO3 per milliequivalent. So they get that. And then they're going to add in the H plus and the OH minus. I think it continues on the next page. So it continues and says, yeah, they did the H plus, now they're doing the OH minus, and all things told, it kind of sums up nicely right here. The alkalinity equation for just carbonate alkalinity is going to be that equivalent of CO3 2 minus plus the bicarbonate plus OH minus minus the H plus. So when we get all those in the same units as CaCO3, they'll report here. And one thing you can notice is that this H plus, we're at a very basic condition. It's a very small number. It's minus 5 times 10 to the minus 6. So it's pretty much rounding compared to even how much of the OH minus we have. So it's a very, very small, negligible number. Is not going to show up in the amount of decimal places they're keeping here for sure. So it's really at a basic pH, it's just kind of not there. If we're doing it at a very acidic pH, it's going to be over here. And so we've got somebody online saying the rounding difference, the carbonate ion, I think that's for the previous stuff. The rounding difference probably made the difference. So, yeah, thank you. Okay, so how do we soften the water then? Kind of wanted to build all that up, describe what the alkalinity is, get some practice in. We might have to resume this next time, but essentially there's two ways we can soften water in terms of removing all that 2 plus, 3 plus kind of stuff. The first would be ion exchange processes. We could go into some detail about how you might design ion exchange, how the materials work, but on the basic premise is you can have these resin type materials, which are maybe it's like a polymer that water kind of can absorb fairly well into, and it's essentially going to be some organic molecule matrix that has a lot of loosely bonded sodiums. Technically, you could also have an anion exchange, so this would be a cation exchange. You could have anion exchange. Basically, you're going to have some of this resin material that's loaded with single ions that have single charges, right? So Na plus. And what's going to happen when it meets water that has calcium or magnesium is we design them so that they have a thermodynamic favorability to get rid of the sodiums in exchange to take a calcium. So that's what we see here. We are taking 2 calciums and releasing 4 sodiums. So we've got a calcium here. Now, at the face value, you might say to yourself, well, it's the same amount of charge. You know, we're not violating the charge neutrality principle. But the fact that we are calculating our hardness typically on the basis of multivalent cations, this is a net benefit, right? So we can do the cation exchange that way and get a good benefit, and it's going to reduce the ionic strength. If we remember, the ionic strength is a function of the charge squared. So we will definitely reduce the ionic strength. That's going to reduce the hardness and many of the characteristics that we don't like about hardness, including the mineral deposits, right? Because sodium doesn't tend to form mineralization deposits of any sort. Sodium chloride, for example, is extremely soluble in water, and there's just not very many other minerals that would form a solid in water with sodium. Calcium, on the other hand, will precipitate pretty readily, calcium hydroxide or other stuff. Okay, so that's one aspect, ion exchange. That's pretty neat, can do a lot for us. The other one that is a little bit more suited to continuous processes, large scale things, because you're eventually going to run out of your resin, going to have to find a way to recharge that. Maybe there's ways to heat it or acid-base treat it or something and re-exchange in a controlled manner in a solution you want. The other process would be what we call lime soda ash processes. So, little pictures here to to portray that. So essentially what we'll do is we will add what's called slaked or hydrated lime, so calcium hydroxide. So we're adding calcium, and then we're going to add this soda ash, which is sodium bicarbonate, Na2CO3. And by adding these, you'd think that, wait a second, we're just adding a whole bunch of stuff. Why are we adding stuff to the water? How's that going to do anything? Well, we're going to manipulate this solution, we're going to manipulate the pH, and we're going to go stepwise to remove different aspects, adjust the pH as needed. And at the end of the day, we can get hardness down to about 40 milligrams per liter when expressed as CaCO3 by adding these compounds. So there's precipitation reactions involved, there's degassing of CO2 involved, there's different stuff involved here, and I want to take a look through that. And we're going to, again, follow another book example. This time I'm not going to have you attempt it, but we'll just kind of walk through it ourselves. So really, water softening with this lime soda ash process is a 5-step plan to soften your water. Not going to lose you any weight or anything like that, but it could soften your water. So the first thing they're going to do, first step is remove the CO2. So removing any excess CO2 dissolved in the water. You could also look at that as removing H2CO3, right? So in order to do that, we're going to add this lime, right, that calcium hydroxide. That's because we have this reaction that's in equilibrium with that calcium hydroxide is in equilibrium with CO2 to form water and calcium carbonate, CaCO3. Now this is a solid, right? So if we have a lot of CO2 in the water, then we can add the lime and we'll get this solid forming. Okay? Typically, we have a lot of CO2 in the water, especially if it's low pH. So you could add calcium hydroxide to that, and functionally that's actually going to be a basic, right? So essentially one thing we're doing here is adding a base, so it should raise the pH, and that calcium will then, that lime will react in such a way where we are forming calcium carbonate solid, and this, since it's a solid, will precipitate. Okay, so that's a way to, when we see something precipitate like that, we say that's removed. Okay, because we can just take the solids right out of solution. So then next step would be to be removing the calcium carbonate hardness. Okay, calcium carbonate hardness is talking about any amount of hardness that we can attribute to what we would call calcium carbonate. So we have, we recognize there's like the carbonate alkalinity. Well, we have this calcium carbonate hardness. I'm going to jump forward for a moment, show us a little graphic, and we'll kind of come back and forth a little bit to it. That I think will help us understand a little bit about that process. So if we think of total hardness as this overarching line here, we have hardness. It's comprised of a few things. Okay, we have calcium, essentially, and magnesium that are contributing. In most systems, that's all we really have. Yes, if we had aluminum, that would be contributing hardness. But for most natural waters that we're just simply treating for use and we need to reduce the hardness, calcium and magnesium are basically everything. So we have some calcium that is related to our carbonate system that is essentially joined with the buffering of the alkalinity, and some that is not. So of our calcium, we might have some cutoff where some of the calcium is associated with bicarbonate, and some of it is just freely in the system. And we're going to differentiate those two things as calcium carbonate hardness, then calcium non-carbonate hardness. Okay, I'm going to back up here, try to make some sense out of that. So we have a reaction where we can take calcium and bicarbonate, in this case 2 bicarbonates, and our lime again. So if we are adding this lime, then we're going to be able to remove more CO2 essentially, but in the form of bicarbonate by precipitating more calcium carbonate hardness, or excuse me, calcium carbonate solids, right? So again, we have a solid here, that means it's removed. So essentially what we're saying is, with the chemical reaction, if we make it favorable, as in we have a lot of calcium around, we can scrub out a lot of that alkalinity, a lot of that carbonate. Okay, so in a weird way, we're adding hardness by adding this calcium, but it's because we are pushing this reaction, which is normally in equilibrium, we're pushing it that way by adding the calcium in the sense of lime. So that's what we mean by, when I flip forward, that calcium carbonate hardness. That is hardness that we can remove based on that reaction with bicarbonate. Okay, so by manipulating that equilibrium, we push it into the solid, then remove the solid out of the water. Okay, so it feels backwards, feels counterintuitive, but we can do it that way. Now, the next step would be to remove the magnesium carbonate hardness. In the graphic here, the carbonate hardness does not extend all the way over, but there's no reason it couldn't, right? It could, hypothetically, extend all the way out there, right? And then we would have all of our calcium would be calcium carbonate, because we just ran out of calcium before we ran out of carbonate. Then we have some portion of magnesium. We could have some magnesium carbonate hardness. Of course, if we put this all the way out here, then we'd have to redraw that and nix that, and then we'd have a magnesium carbonate hardness, right? In our hypothetical example there. So backing up then, we can remove magnesium carbonate hardness by kind of doing the same thing. And this is because we can precipitate magnesium in terms of magnesium hydroxide, MgOH2. That's favorable. Again, when we add a lot of lime, we are getting more of the calcium carbonate, but also the magnesium removal. Okay, this just turns out the way the chemistry works. We can push it that way by, again, adding our lime to push it that way. Okay, so the other stuff here just was naturally hanging out. We have some magnesium and we have some bicarbonate. And remember, the principle of charge neutrality means these two are normally kind of balancing each other, right? In fact, if we have one Mg2 plus to 2 CO3 minuses, HCO3 minuses, those balance. So by adding a bunch of lime, essentially we're adding a bunch of Ca2 plus. We are, I guess, then we're removing some of it back. We are allowing for all of the rest of that stuff to precipitate while keeping the charge neutrality. Okay, after that, then we can get on to remove the non-carbonate hardness. We've essentially stripped most of the carbonate out of the solution. We are left with just a little bit of calcium and or magnesium that's no longer correlating, no longer able to be removed in association with the carbonate that's in the water. So here, we're left with just calcium, and in a strange sort of a way, we can then add some carbonate to remove that calcium. Okay, so it starts feeling really backwards until you realize what we've been removing as solids is we're constantly removing the calcium we're adding back out, okay? Or at least most, if not all of it. In fact, usually we're getting more than what we add back out. So in this case, here we're adding the soda ash, and this is Na2CO3. And if you notice here, Na2 is not going to contribute to hardness, right? Because that's just going to be +1. Na plus is going to be a non-hardness species. So we add, to target our remaining calcium, we add this soda ash so that we push it towards, we give it plenty of carbonate to react with the remaining calcium, to push it over there to remove as much calcium as we can in terms of CaCO3. And yes, we do get some Na2+, just like the reaction with our ion exchange, by the way. We end up adding some sodium back in place. Lastly, we can do the same type of thing with the magnesium non-carbonate hardness, where we, again, no longer have enough carbonate in the system. But at this point, we also have pretty much no calcium either. So we end up adding a little bit more calcium because this particular reaction likes to go when it's making both magnesium hydroxide solids and the calcium carbonate. Because we also, have to take care of the carbonate that we're adding. So because when we get magnesium hydroxide, that's not accounting for any of the carbonate that we just that we're adding with this guy. So we end up adding a little bit of both. We can remove a fair bit of the magnesium, and all of this put together, we have reduced our hardness. And backing up a step, I said we can only really practically reach about 40 milligrams per liter as CaCO3. And we see now why, because these are all equilibrium reactions. And while we can force them to the right, this last step in particular, we can only force it so hard, there's just going to be some residual. But by that point, if we were to scroll back in our mind or the different lecture slides, 40 milligrams per liter as CaCO3 is pretty soft water. Okay, so that's within the classification of soft water. And we probably wouldn't even want to go all the way to purely, deionized water. That actually probably wouldn't be good for health and everything. Okay, so that's the 5-step plan. I don't know why this stayed on this slide. So there's an example. We only just have a couple minutes, so I'm just going to describe the example, then we'll head out, and we'll probably pick up here and then talk about the Flint water crisis next time. So this example is giving us some table that's describing different amounts of each of these, and then it's going to ultimately suggest us that we take that table and say, okay, well, if we have some utility that's treating some amount, given these parameters, then the questions are, okay, well, how much lime and soda do we have to add to soften the water appropriately? So then we'll have to go back and think about, okay, how much are we using for this step? How much are we using for this step? And we can calculate each of those with that process of, okay, here's the first one, and we can really make good use of this table here, considering where they're all at. Okay. With that, the last thing I'm going to say is I will post on Moodle, I'm going to post a quiz for the cryptosporidium outbreak paper, and I'll have it due probably by the end of the week, or maybe by the end of Thursday this week. You'll have just a few minutes to do it once you start it, and that'll just kind of be a participation checking on if, if you've read it and what you got from it. So if you have not yet, take a look at that, and I'll send out an email reminder that I'm posting that. So I'll see you on Thursday.